Good morning. Good morning to all of you. Yes, I hope you are writing your assignment. In the meantime, you are supposed to study all these materials, whatever we are sending. Don't forget. Good morning, Sharanya. Okay. Yes. Good morning, Usha. Last class we have discussed about the two Maxwell's field equations. Right now, Farana, Shafin. Good morning. Last class we have discussed about two Maxwell's field equations. Today I will send the whole notes. Whatever it has been covered today also, that I will send it. Voice is too low. Okay, now you are hearing, I think it's so. Right? Okay. Yes, listen now. Is it audible now? Now I'm asking you, is it audible?
Yes, sir.
Okay. Okay, right. Listen now. The third Maxwell's field equation I supposed to derive, and the fourth one today. And if possible, the physical significance of all the four equations. Okay, very important chapter, very important topic, full of mathematics only. No other way. You had to take some sheets of paper, write and practice at home. Okay, third Maxwell's field equation. Derive. We are not asking third Maxwell's equation. We are writing derive. Del dot B is over now. Second one. Second one is over. Del dot B. This is del cross E. Del cross E is equal to minus del B divided by del T. Partial derivative of magnetic field. B is the magnetic induction. H is the externally applied magnetizing field. There is a relation between B and H taken from your second PUC concept. Not this one, of course. This derivation now we are supposed to learn it. So del cross E is equal to minus del B divided by del T. So many number of times that we are going to make use of Stokes theorem. Now, especially today, last derivation that we have come across about the Gauss theorem, Gauss divergence theorem. Now I will going to make use of Stokes theorem. So carefully you listen, understand the concept. Now I will going to make use of this one. I supposed to derive this concept. I supposed to derive. Now, for this purpose, I will going to take up Faraday law here. Faraday's law. You are aware of Faraday's law. Even in high school level, you have studied the Faraday's law basic. Then in detail, you have studied in your second PUC. Whenever there is a change in the magnetic flux linking with a coil, if there is a coil is present like this. Okay. So this is a coil, an ordinary coil. If you are inserting a magnet here now, the magnet, if you are go on putting inside this coil and removing like this, putting like this and removing like this inside the coil, if a magnet, if it is moving and if it is moving with respect to time here now, rate of change of magnetic flux is existing here. Due to that one, here there is an induced EMF, an induced current here now. If you want to see that one, we are connecting a galvanometer. Galvanometer shows the deflection. If the magnet, if it goes inside here, galvanometer shows one side deflection. If you are removing that one, it will show the other side deflection. This one you have studied in your lower classes. Faraday first law, Faraday second law. Whenever there is a change in the magnetic flux linking with a coil, there is an induced EMF and induced current in a coil. The induced EMF or maybe the induced current, whatever it is flowing here, it is directly proportional to the rate of change of magnetic flux. There is a rate of change of magnetic flux. Okay, taken from your second PUC. Because
Excuse me, sir.
yes,
Sir, can you explain once again from the beginning?
from the beginning, this is the beginning class, beginning idea only.
Sir, this
I
only,
suppose
sir.
I suppose to derive this one. This is Maxwell's third equation we are supposed to derive. To derive this equation, we are supposed to consider Faraday's law. That is taken from your second PUC portion, that Faraday's law. Based on this Faraday law that we are supposed to derive. I told you already, okay, Gauss theorem, first we have used Gauss theorem. To derive the first law, we have used the Gauss theorem. For the second one, we have used the Savard-Biot law, right? The third one, we are using the Faraday's law. For the fourth one, we are using the Ampere's circuit law. These are all the four important concepts that we have already learned in your lower classes. Then we had to use it. What this Faraday law that states? It states that if you are choosing a coil like this is a coil connected to a galvanometer. If you are introducing a magnet here, these are magnet, North Pole and South Pole. As you are introducing a magnet like this, if you are introducing a magnet like this, with respect to this coil, there is a change in the magnetic flux. Due to that one, here there is an induced EMF, an induced current here now. Therefore, galvanometer shows one side deflection. If you are keeping the magnet inside here without movement, if it is said to be at stationary, the magnet is not moving now. Therefore, here there is magnetic flux, but change in magnetic flux which is not present. The change in the magnetic flux linking with the coil is equal to 0. Change in magnetic flux. But there is a flux. Constant flux is there, but there is no change in the magnetic flux. If you are introducing a magnet, the magnetic flux linking with the coil is go on changing. Due to that one, here there is an induced EMF and current. It has been shown by the galvanometer deflection. If you are keeping the magnet here, no change in the magnetic flux. Therefore, galvanometer deflection slowly it is coming back to 0. If you are removing the magnet from inside the coil to outside, if you are removing the magnet like this, now the galvanometer shows the other side deflection because the EMF and the flux, whatever it is producing here, it is oppositely directed. Hence, the current is also flowing in the opposite direction. So that is Faraday's first law. Whenever there is a change in the magnetic flux linking with a coil, there is an induced EMF. If there is no change in the magnetic flux, there is no induced EMF. Second law, it states that. Second law. First law, whenever there is a change in the magnetic flux, there is an induced EMF. If there is no change in the magnetic flux, induced EMF is equal to 0. Second law, it says that the induced EMF is directly proportional to rate of change of magnetic flux. Induced EMF is equal to rate of change of magnetic flux. E is equal to d phi by dt. But one more law is coming as a Lenz's law. It says that if the flux is changing in one direction, then the induced EMF that takes place in the opposite direction. Therefore, we can write E is equal to minus d phi by dt. The negative sign indicating whichever the direction, the flux that is existing, in the opposite direction, EMF is produced. All these things are borrowed from your second PUC portion. Now I will take up your degree class concept based on this. So I will going to make use of Faraday law here. From Faraday's law. Along with me, you are supposed to take some sheet of paper and you have to write. Afterwards, anyhow, I will send the notes. You can copy that notes. Don't keep that notes as it is. Okay, you have to copy that. Right? Because all these things, if you are reading, you cannot understand. And you cannot write at the time of exam also, just if you are reading all this concept. You have to write. Many number of times you are supposed to practice by writing at home. So from Faraday's law, it says that induced EMF in a closed loop is given by, what is that? Induced EMF is equal to minus, here d phi by dt I have written, but here partial derivative that I am writing. This is lower class concept. Now let me take up the partial derivative like this. Del phi by del t. What is that flux? Flux is equal to here. Flux is equal to where? Flux is given by, again taken from your lower class standard here. Go for the electrostatics. Flux is equal to integration of E dot ds. Flux is equal to integration of E dot ds. I will write that. Electric flux, of course. Electric flux is equal to integration of E dot ds. E dot ds. This is electric flux. But if I want to write the magnetic flux here, I can write instead of E, I can write B here. B dot ds. Electric flux is E dot ds. Magnetic flux is equal to B dot ds with an integration symbol. It takes as a surface integral here. I will write S here. Surface integral S. Okay, yes, B dot ds. Therefore, this EMF is given by, this equation becomes EMF is equal to how much? Minus del by del t of this one we are supposed to write. Integration of surface integral of B dot ds. Let us take up slowly, no problem. The dot, everything carefully had to write. B dot ds, because it is a dot product, scalar product. Now I will take up this one inside the here now. Therefore, induced EMF is equal to minus, okay, integration of S here, del B divided by del T. I can write del B divided by del T dot ds. As it is. Just I have taken this one inside. Clear? Follow this. Now, I will going to consider EMF in the other way. I will going to consider EMF in the other notations. What is that? EMF means it is an induced EMF. This is induced EMF. This induced EMF can also be written as work done in, taken from your maybe again second PUC concept. Work done in a closed path, in a closed circuit if you are choosing. Define EMF of a circuit. Define. You remove this induced, no problem. Define EMF, electromotive force. Electromotive force may be defined as it is a work done in moving a unit charge around a closed path. So that is a definition that we are going to frame. So I can say the induced EMF is equal to work done in moving a unit charge or unit positive charge, no problem. A unit charge or unit positive charge around a closed path. Around a closed path. That is a definition here. This is the definition for induced EMF or EMF. So here E is the induced EMF, therefore I have written the definition again. Therefore, I can write this induced EMF E is equal to, using this definition taken from the lower class again, I can write integration of E dot dl. Therefore, I will write using this E dot dl. E dot dl. This is a line integral because it is a closed path is present here. There is a closed path. Through that path, whatever the unit positive charge if it is flowing, how much is the work done by the system, that itself is called by the name the EMF. So E dot dl. That E dot dl over a closed path I suppose to consider here. Therefore, I will write a round mark here. A small round mark means it is a closed path. A closed path. Therefore, it is a, if you are starting from one point, we have to come back to the same point here. total EMF generated is given by E dot dl, where E is the electric field. Where E is the electric field, don't forget. E is called by the name the electric field intensity or electric field. Electric field or electric field intensity. Use this concept here. Therefore, this expression becomes substitution. We are supposed to do it. Therefore, integration of closed path E dot dl is equal to this one as it is, I will write minus integration of surface integral del B divided by del T dot ds. This is surface integral. This is a line integral. This is a line integral. This is surface integral. We cannot equate those two, but we have written equation is equal to, it has been written. But this is in terms of line integral. This is in terms of surface integral. Double integration, it is present here. Here it is single integration of a closed path. This is of a closed surface area. Now I want to convert this one in the form of surface integral. E dot dl, whatever E dot dl is present, let us convert that one in the form of E dot ds. In the form of E dot ds, I suppose to convert here now. Using what? Either Gauss theorem or Stokes theorem we had to take up. Which theorem we had to use it? Carefully we had to choose it, because we want to convert the line integral in the form of a surface integral. L to S we had to convert. For that purpose, I will going to take up Stokes theorem. Yes, okay, blindly. L to S if you want to convert, S only we have to choose, that is Stokes theorem. Use this Stokes theorem, apply this. L to S I have to convert. Starting with S is said to be the Stokes theorem. Let us go for Stokes theorem here. Apply the Stokes theorem for this. Apply Stokes theorem. As we are applying the Stokes theorem here, I can write here it is E dot is there. E dot product converting in the form of cross product. Dot product convert in the form of cross product. Dot converts in the form of cross. Scalar product converting in the form of vector product. Del cross E, you are going to get del cross E dot ds is equal to same thing. Then we can equate, because both are surface integrals, we can equate. Okay, I will take up the next page now. I will turn the page now. Okay. Yes. What is that? Using the Stokes theorem. From Stokes theorem, what it says, integration of closed path of E dot dl is equal to surface integral of del cross E dot ds. Dot ds. Okay, this is Stokes theorem. Therefore, previous equation, whatever we got this one, I had to write this one. Therefore, can I show it again? This expression. Right hand side as it is I will write. Left hand side only that I will going to convert in the form of line integral to surface integral using the Stokes theorem. Okay, so therefore this is surface integral of del cross E dot ds is equal to how much? Del this one minus integration of del B divided by del T dot ds. Now we can equate both the sides because both are surface integrals. Both are surface integrals. ds is here, surface integral, surface. I can remove all these common things, whatever it is present on both the sides here. Remaining only the content only that I will going to write. Integrand, whatever it is present, that one only that I will going to write it here. Therefore, here del cross E is equal to minus this one del B divided by del T. This is the equation that we require. This is Maxwell's third equation. 4 equations are there. Out of that, the 3 equations, it has been derived so far. Easy. Only thing is you require some amount of practice sessions. Okay. If you don't do the practice sessions at home properly, at the time of examination, you will mix up all the 4. So don't do that one. Confusion will be there. Mixing up all the 4 and writing the 5th equation which is not existing. Then we will give you 0 marks. So don't do that. Only thing is do the practice at home carefully. You have to practice. You have to write all these concepts clearly, properly at the time of examination with dot, cross, surface integral, line integral, closed path, everything you have to write it carefully. Okay, this is the third equation, Maxwell's third equation. It has been derived. Now I will going to take up the 4th equation now. 4th equation, no other way, we have to use Ampere circuital law. Already we are aware of that, Ampere circuital law. Okay, I told you already, B is the magnetic induction, H is the magnetizing field intensity, whatever it is active. There is a relation between B and H. Second PUC has studied all these things now, magnetic induction, externally applied magnetizing field, susceptibility, all these ideas, magnetic materials, you have studied all these concepts. So here, a little bit extra knowledge that we are supposed to learn. Okay, using your the basic mathematics. So what is that? The 4th equation. Maxwell's 4th equation. Derive. This is a little bit lengthy, but you can write, no problem. Derive del cross B is equal to mu into J is the current density. J is the current density. This is permeability. Mu is equal to mu naught into mu r, where mu naught is called by the name the absolute permeability. Mu r is called by the name relative permeability. J is current density plus del D divided by del T. Forgotten already what is that D? Displacement current. Heard about displacement current, conduction current, displacement current, the current density. This one we can ask, or we can ask, or derive. Instead of B, we can ask H also. Del cross H. They are one and the same. Okay, B is equal to mu into H. That's all. So that is equal to here J into, here we are not going to get the mu here. So J plus del D divided by del T. This one we are asking for about maybe 4 marks or 5 marks. This itself that we are asking. But this particular 4th equation only that we are asking, either for 4 marks or 5 marks, depending upon your question paper pattern. Okay. I will going to start with Ampere's circuital law. From Ampere's circuital law. Ampere's circuital law. Don't forget, Ampere's circuital law is inconsistent, which is having a wrong concept. Then it has been corrected by Maxwell by introducing the another current called by the name the displacement current. Not only conduction current is present, along with that one more current is flowing, that is called by the name the displacement current. Therefore, the total current is said to be I plus ID due to the change in the magnetic flux. Okay, anyhow, I will send all the notes today. You go through all the concepts properly. From Ampere's circuital law, what it states? It states that integration of closed path L line integral B dot dl is equal to, if it is air medium, okay, then I can write mu naught. If some other medium, I can write mu into I. Vacuum, if it is present, you can write mu naught. If some other a material is said to be existing, mu into I. Okay. This can be replaced by H. Okay, this can be replaced by H. Right? I can write integration of H dot dl is equal to, here it is I. If they are asking in terms of B, you introduce mu. If they are asking in terms of H, you remove this mu. Mu value is equal to 1 here. If you are using H, mu value is equal to 1. So in this case that I have used, mu value is equal to 1. H dot dl is equal to I. I is equal to H dot dl, closed path. Of course, line integral, closed path. Closed path here, over a line integral. H dot dl is equal to I. H dot dl is equal to I. Use this concept further. Further, we are supposed to use it. What is that? This is Ampere's circuital law that I have written. Correct? Okay. But current density J is equal to how much? J is equal to I by A. You are aware of that one. So let me write current is equal to how much in terms of J. I is equal to how much? I means current, J means current density, is equal to, over a closed path, surface integral J dot ds. J dot ds, where J is the current density, ds is the surface area here, over a surface area S, I is the current. Therefore, current is equal to integration of surface integral of J dot ds. Use that one here. Therefore, integration of closed path line integral H dot dl is equal to surface integral of J dot ds. J dot ds. Correct? Again, the problem is, I want to equate these two now. I want to equate these two, but this is in terms of line integral. This is in terms of surface integral. I want to convert line integral in the form of surface integral. Therefore, I supposed to apply which theorem? Stokes theorem. Apply the Stokes theorem. So let us apply the Stokes theorem here, because I want to convert line integral in the form of surface integral. Then we can equate those two. So let us apply the Stokes theorem. So as you are applying the Stokes theorem here, the line integral converts in the form of surface integral. How we are going to write? Okay. Shall I turn the page now? Okay, I will keep this one as it is. First, let us apply the Stokes theorem here. From Stokes theorem. From Stokes theorem. Okay. Yes. What is that? Line integral of h dot dl is equal to, convert in the form of the surface integral. Surface integral dot becomes cross here, del cross h dot ds. This is using the Stokes theorem. Apply this one to here. Then you write this equation. Therefore, integration of this means this. Del cross h dot ds is equal to surface integral of j dot ds. Right. Okay. Now we can equate both the sides, left hand side as well as right hand sides, that we can equate now, because both are written in the form of surface integrals. Both are written in the form of surface integrals. We can equate the integrands. We equate that. Therefore, del cross h is equal to j. Del cross h is equal to j. This is holds good only for the steady current which is flows in the circuit. It is not applicable for your AC current or steady current if it is not flowing. Capacitors. Capacitor, the two plates are present. Okay. Between the two plates of the capacitor, no current is flowing. DC current is equal to 0. If the DC current is equal to 0, then we cannot apply Ampere circuit law. Here we can apply the Ampere circuit law closer to this conductor. I already explained. Due to that one, Maxwell, he has invented one more current called by the name of displacement current. This is conduction current only. This is not applicable everywhere. Everywhere this is not applicable. There is an inconsistency in the case of Ampere circuit law. This inconsistency, it has been corrected by Maxwell. Maxwell, he has corrected that inconsistency. Okay. Now let us take the divergence here now. Taking divergence, whatever I explained now, I will write in the form of mathematics now. Taking divergence on both the sides. For this, I can write del cross h. You know about what is divergence. Del dot is equal to del dot j. Both the sides that I have taken the divergence. But this value is equal to 0. This value is equal to 0. This implies del dot j is equal to 0. Whatever I explained now, between the two plates of a capacitor, current is equal to 0. Since the current is equal to 0 here, I can say that magnetic field must be equal to 0. Current density is equal to 0 here. It says J is equal to 0. There is an inconsistence. This is mathematically it has been written. That inconsistence of Ampere circuit law, it has been written mathematically. Okay. So therefore, del J according to your equation of continuity from equation of continuity. Already we have derived this one now. Equation of continuity. I can write del dot J is equal to minus d rho divided by dt. It is a charge density. Don't forget, rate of change of charge density. D rho divided by dt with a negative sign. Clear? I told you already, Maxwell, he has corrected that inconsistency. Inconsistency. It has been corrected by Maxwell. Called by the name the Maxwell Ampere Maxwell second, right? Or Maxwell Ampere circuit. That is after correction, that is. So therefore, del cross H, whatever we got the equation here now, the del cross H, there is an inconsistency. There is a mistake in writing this because of all these facts and figures. Therefore, this del cross H, which is not only equal to J, along with that one more current density is present called by the name displacement current density, either small d or capital D, whichever that you want to write, you can write JD. Therefore, del cross H is not equal to J here. Actually, del cross H is equal to J plus something else. This is conduction current density. This is displacement current density. J plus JD, where JD is said to be the displacement current density. Now you take the divergence like this. I have taken the divergence here now for this equation. Like that, let us apply the divergence for this formula also. So take the divergence. Again, check it out. Taking divergence on both the sides. What you are going to get? Del cross H is equal to del dot J plus JD. J plus JD. I have taken the divergence on both the sides. Here also divergence it has been taken. But already we know that del cross H is equal to 0. Therefore, this value is equal to 0. This value turns out to be 0. If it is equal to 0 here, I can write this can be written as del dot J plus del dot JD, right? Del dot J, I have written all the steps here, plus del dot JD. Therefore, del dot J is equal to how much? Del dot J is equal to how much? It is equal to minus of, taken to the other side of the equation, minus of del dot JD. But del dot J is equal to how much? But del dot J is equal to how much? Minus d rho divided by dt. Clear? See that? Hoping that you have written every concept properly, all the ideas. because giving a notes is different. Explanation given is said to be something else. Keeping the notes and reading, not so easy to understand. Right? So therefore, next step. What is that? But del dot j according to continuity is equal to minus del rho divided by del t. Therefore, del dot j is equal to how much? Is equal to this minus del dot jd, that is also equal to minus d rho divided by dt. Del rho divided by del t. Okay. Now negative sign get cancelled on both the sides here. This implies del dot jd, displacement current density, is equal to del rho divided by del t. Use the Maxwell's first law. Already you know that. Maxwell's first law. According to Maxwell's first law, rho is equal to del dot d. Del dot d is equal to rho. So therefore, del dot jd, this value can be written as del by del t of rho value. I supposed to do the substitution here. How much? Del dot d. Therefore, del dot jd is equal to, apply the concept. I will take up this operator outside here. Del dot, I will take the differentiation here. Both the sides we can equate, and we can write jd is equal to, we can equate this is equal to this, del d divided by del t. This is the value of jd, don't forget. Means displacement current density, it has been written. Therefore, del cross h is equal to j plus jd. Somewhere else we have written now. Yes. All right. Same equation that I have written becomes, substitute this value here. This value we had to substitute here. So therefore, del cross h j plus, this value is del d divided by del t. Because jd is equal to del d divided by del t. This is fourth law of Maxwell's field equation. Maxwell's field equation, fourth law. Okay, all the four laws it has been written. Now another about maybe 5 minutes enough to take up the physical significance of Maxwell's field equations. If we are asking, write the physical significances for about 2 marks or 3 marks, you get ready for that also. Okay, one by one, I had to take up just another 5 minutes. Only the basic physical significance. Means what is that meaning, where we are using, why we had to study all those concepts. Equation number 1, equation number 2, equation number 3 as well as 4. Okay, yes. Physical significance. Four laws. First law, it says that del dot D is equal to rho. Del dot D is equal to rho. This is Maxwell's first law. Maxwell's first law. Del dot D is equal to rho. What is that meaning? What is that physical significance? This equation represents what? What is that equation represent? The net outward flux of an electric displacement. The net outward electric flux. The net outward electric flux of an electric displacement through a surface, which is enclosing a volume is equal to the net charge contained in that volume. Means charge density, of course. Okay, number of charges divided by that volume is called by the name the current density. Again, I can say that the net outward flux of electric displacement vector, the net outward flux of electric displacement vector, that is capital D, through a surface enclosing a particular volume is equal to the net charges contained with that volume. How many charges contained with that volume? That is equal to that. That is equal to this is equal to this. What is that concept? The lines of flux either enter or leave the closed surface due to the presence of either a positive or negative charge within the surface. So there is a area is present like this. The flux may be passes through like this, or it may be passes through like this. Either it enters or it is exit. It is due to the number of charges, how many they are present here. Now, in that closed path, how many number of charges are present, it is all depending upon that. That is a first law significance. Second law, number 2, del dot B. B is the magnetic field, don't forget, it is equal to 0. Del dot B is equal to 0. You know about electrostatics. Electrostatics, maybe a plus Q charge is present, maybe a minus Q charge is present. Correct? No. Plus Q and minus Q are separated by a very small distance, is called by the name the electric dipole. If I'm keeping like this now, plus Q and minus Q separated by a small distance, these are called by the name the electric dipoles. They are called by the name the electric dipoles. Electric dipoles. This is isolated charge. Isolated charge. This can be happening, isolated charge, isolation, only plus Q is present, only minus Q is present, or both together is present here now, called by the name the electric dipole, separated by a very small distance, maybe 2a or small, 2l, no problem. But in the case of a magnet here, is it possible to get only the north pole? No, we cannot. Isolated north pole, isolated pole, we cannot get. Isolated south pole, only one pole magnet, is it possible to exist? Cannot be. It is existed in the form of only a magnet containing a north pole and south pole. This is called by the name magnetic dipole. Magnetic dipoles are existing, but magnetic monopoles are not existing. Magnetic monopoles are not existing. Electric monopoles are existing, no problem, means single charges. But here, magnetic monopoles are not existing, but magnetic dipoles are existing. So that is the meaning of second law. Del dot B is equal to 0. Means if you are choosing a surface area, and if you are keeping a magnet here, north pole and south pole, now the total magnetic flux, whatever it is coming out, is equal to 0. The flux is equal to 0 because north pole is also there, south pole is also there. The outward flux is equal to 0. Or inward flux also. It is always equal to 0 due to a magnet. Because magnet is containing both a north pole as well as south pole. If you are choosing only the north pole, outward flux will be there. If you are choosing only the south pole, inward flux will be there. But both are present here, the total magnetic flux is equal to 0. Taken from your second PUC, this concept. This is significance. Third law, number 3. Third law. What is that third law? Del cross E is equal to minus del B divided by del T, which means to say that the electromotive force, E means electromotive force, around a closed path is equal to the negative rate of change of magnetic flux. Negative rate of change of magnetic flux linked with that path. Okay. Fourth one, del cross B is equal to, if I'm writing H here mu is not coming. If I'm writing B here, mu is coming. J plus, okay. So if it is written as H, mu will not be there. If I'm writing B, mu will be there. Mu is a constant. Okay. The magnetomotive force, here electromotive force, here it is a magnetomotive force. Electromotive force, magnetomotive force around a closed path is equal to the sum of the conduction current density and this is displacement current density through any closed path. So read that much, it's enough. It's enough. So one concept, it has been finished. Next class that I will going to take up some other derivations. Some other derivations I supposed to take up in the next class, that is propagation of electromotive force, or electromagnetic waves. The propagation of electromagnetic waves in a dielectric medium means velocity. Derivation for velocity of propagation. Still more derivations are there. Okay, a little bit lengthy derivations. Still it is existing. Okay, we had to prove that C is equal to, you know about that, C is equal to 1 divided by square root of mu naught into epsilon naught. V is equal to square root of under the 1 divided by mu into epsilon. This is for velocity of light in any medium. This is velocity of light in air or vacuum medium. You know about that. Mu naught value is equal to 4 pi by mu naught, of course. 4 pi by mu naught is equal to 10 to the power minus 7. Mu naught is equal to how much you can write? Mu naught by 4 pi, I'm sorry. Mu naught divided by 4 pi is equal to 10 to the power minus 7. I'm sorry. So mu naught is equal to 4 pi into 10 to the power of minus 7. Epsilon naught is equal to 8.854 10 to the power minus 12 farad per meter. Again, all these concepts borrowed from your PU level. Mu naught by 4 pi, 10 to the power minus 7, epsilon naught value 8.854, 10 to the power of minus 4. Anyhow, go through all this concept. Next class that I will take up these derivations. Velocity of light in air medium, velocity of light in any other medium, dielectric medium. This is in dielectric medium, glass, water, like that. This is in air medium. This is Maxwell's derivation again. This is called by the name of the Maxwell's derivation. Okay. Any doubt is there, you can ask. Any doubt that if you are having, you ask. Okay, go through